For this problem, we're being asked to find the limit as x approaches 0 of the natural log of cosine of 2x, all divided by 4x squared. And we note that if we evaluate it the way it is, we would have the natural log of cosine of 2 times 0. And notice I'm using grouping symbols to clearly show the composite of that function. Natural log's outside, cosine's in the middle, and 2 times 0 is inside of the cosine, all over 4 times 0 squared. And if we work our way in the numerator inside out, we've got natural log of the cosine of 0 divided by, of course, 0 squared is 0, 4 times 0 is 0. And now the cosine of 0 we know is 1. And then the natural log of 1, that is e to what power gives me 1, is 0. And we end up with 0 over 0, or indeterminate form, which means we can't find the limit by direct evaluation, but we can apply L'Hopital's rule and take the derivative of the numerator over the derivative of the denominator and see what that gets us in terms of a limit. So we're back to limit as x approaches 0. Now, working on the derivative of the numerator, again, it's important to understand the composite. The outer function is natural log. So the derivative of natural log is 1 over its function, which was cosine 2x. Then applying chain rule, working our way in, the derivative of cosine 2x would be negative sine 2x. And then one more layer of chain rule, the derivative of 2x is 2. So all of that is the derivative of the numerator. Luckily, the derivative of the denominator is much easier. That is 4x squared. We can apply the power rule and get 8x. Now if we clean this up a bit, let's take a look at this numerator and see what we can do. So we still have the limit as x approaches 0. If we put together our sine of 2x over our cosine of 2x, we get a tangent of 2x. So we can take the negative and the 2, put it in front, and then tangent 2x. That'll make the work from here on out go a little easier, all over 8x. And of course we can do a little simplification here and reduce the 2 and the 8 down to 1 and 4. So I guess we better rewrite that one more time and see what we have. So the limit as x approaches 0 of negative tangent 2x over 4x. And don't be tempted to reduce that 2x and 4x, because the 2x, remember, is inside the tangent function, whereas the 4x is outside and all alone. So let's try evaluating now and see if we made some progress and can calculate our derivative, or I'm sorry, our limit. So that would be the opposite, or negative tangent 2 times 0 over 4 times 0. And that gives us negative tangent of 0 over 0. And you have to recall that the value, the tangent at 0 is 0, so we have the opposite is 0 over 0, or another 0 over 0, indeterminate form, which means we can use L'Hopital's rule one more time. But now we're going to work with the opposite of tangent of 2x over 4x and see what we get when we do the limit of that. So we still have our limit as x approaches 0. And the negative will just stay. That's the constant rule. And the derivative of tangent is secant squared 2x. And applying the chain rule then to that, times 2. Denominator, again, is much easier. We just had, let's see, what did we have? We had 4x, so that'll get us a 4. Okay, so once again we can do a little more reducing. The 2 turns to a 1 and the 4 a 2. So regrouping, we have the limit as x approaches 0 of negative secant squared 2x over 2. Okay, so let's try evaluating this time and hope we have a number. So the opposite of secant squared, 2 times 0 over 2. Notice that denominator is constant now, so that's looking promising. Keep in mind the negative is not part of the square, so we're going to calculate the secant of 0 and then square that number, all divided by 2. And secant, recall, is 1 over cosine, so cosine at 0 is 1 and 1 over 1 is 1. So we have the opposite of 1 squared over 2. Square the 1, we get 1, so the opposite of 1 is negative 1 over 2. And we finally, with 2 rounds of L'Hopital's rule, found the limit to be negative 1/2.